So my name's Charles Wood. I lead the Chattanooga Chamber of Commerce, and I would have given you a longer, more boring spiel that mostly talks about everything in that video. But really excited to have some of the folks that are putting a lot of this partnership together. And for those of you that don't know our community, we have a history of public and private partnerships that's gone on for a long time. We've reinvented the city, and EPB's played a big role in that. And so this panel is going to talk about partnerships. We're going to talk a little bit about kind of how this came together and what each of these folks are involved with as part of some of what you just saw. So with that, I'm just going to ask the team to go ahead, introduce themselves, and then maybe a little bit of kind of your role. So.
Hello, everybody. I'm Shaun Gleason. I'm the Director of Partnerships at the Oak Ridge National Laboratory. My primary role there is to build partnerships with industry, so very happy to be on this panel with colleagues. Oak Ridge has 30 plus years experience combined with the industries you have represented on the panel here, so excited to be here, and one of my primary goals is to get technology, basic research, and applied research at the lab out into the hands of industrial users, so this is a great example of that.
Hi, everyone. Good afternoon. I'm Janet Rehberg with EPB. I'm the President of Strategic Initiatives, so I get to roll out a lot of the cutting-edge emerging technologies, such as quantum. And EPB has one of the most advanced automated grid, as well as the world's fastest internet, up to 25 gig symmetric. And so our fiber industry has brought up so much economic benefit to our community. And I think when we looked back, 10, 15 years of our network, it has brought in billions of dollars in economic value and created over 10,000 jobs there. And so that's why we are excited, because part of our mission is always about enhancing our community. And we think that quantum is that next wave that's going to be able to bring that much value, if not more, to our community.
Hi everyone, I'm Rima Alameddine. I'm the Chief Revenue Officer at IonQ, and in my role, I get to work with customers and partners to solve their real-world problems. And what's really exciting about this team is that we are working on real-world problems and bringing our capabilities together to solve them.
Hi, I'm Nick Harrigan. I work with NVIDIA, where I work on how we talk about everything we're doing in quantum computing. And at NVIDIA, we're really interested in quantum computing. We see the accelerated computing that we build as being a key part in developing and actually operating quantum computers in the future. And so I'm here today because we do great work with our partners who are all fantastic about making that vision a reality, and this is a great example of that.
Great, thanks so much. And I guess I should add another thank you, because NVIDIA did an acquisition of an early stage company that was in Chattanooga for a bit. So thanks for that too. Janet, do you want to get us started and maybe just talk a little bit about how this came into fruition?
Yeah, how this fun partnership between the four of us all came together. So, EPB and Oak Ridge have done a lot of projects over the years with our grid. And through, as you saw, 2016 was the first time that EPB and Oak Ridge got to work on quantum through a DOE project, and it was a quantum key distribution for grid security. And this year, one of our greatest assets at EPB is the data that we have. We have, the last 16, 17 years, over a trillion data points that we have as a great asset. And so Oak Ridge, Shaun came to me and said, we have they're great with their supercomputer, the Frontier, and they started to look into the NVIDIA DGX and said, what if we brought an NVIDIA DGX as a partnership and be able to do some grid optimization on the data that you have? And that was early this year. And didn't know that a few months later, as we look at the quantum space, we already had the quantum network at that time, that the benefit of quantum that we saw from the McKinsey study shows that with quantum computing, there's going to be trillions of dollars in the economic value. So our board approved for us to acquire a quantum computer. And back in 2016, when we were working with Oak Ridge, we also worked with a startup company called QWC. And Cubatech helped us build our commercially available quantum network. And Cubatech was acquired by IonQ end of last year, and so that created a whole new relationship with us. And as we're thinking about which quantum computer to purchase, why not buy a IonQ? Because as you think about scalability, we have a quantum network, and part of an IonQ scalability is to be able to network multiple computers, and we wanted to be part of that wave. So right after we announced that we were going to acquire an IonQ, NVIDIA reached out and said, hey, that's exciting news. What could we do to be a part of that? So that's when I reached out to Rima and Shaun and said, hey, we're going to have a great partnership with Oak Ridge with doing some classical computing. We have the NVIDIA DGX at our quantum center, and we're about to have an operational quantum computer. Can we do a grid application project together as a pilot? So that's how the partnership sort of started. Shaun, you want to add to that?
Sure, happy to. You did a great job. Give Jan a lot of credit for conceiving of this idea for this partnership, building on some of the assets that she's already talked about. I did want to mention that we just this year did an experiment, a quantum communication experiment on EPB's commercial quantum network, trying out a brand new technique called automated polarization compensation to help improve the reliability and transmittability of quantum information on a commercial network. So it's a great resource. We do things in the lab and research, and then we can partner with folks like EPB to test these technologies in a real world system. Just a little bit of other history about the partnerships here that I think is interesting. So back in 2012, so Oak Ridge is known for deploying 4 of the world's fastest supercomputers over the last 20 years. One of those was the Titan supercomputer back in 2011, and that was the first supercomputer that we deployed that what we call a hybrid system. So it leveraged NVIDIA GPUs and then CPUs on the same platform. And this was a huge risk, I think, for both NVIDIA and Oak Ridge, but a risk that was very well worth taking, and it paid off, because now all of our systems since then have had more and more GPUs on our fastest computers in the world. So the NVIDIA ORNL partnership goes way back, and now the more recent partnership with IonQ, we have a program called the Quantum Computing User Program at Oak Ridge, and we provide free access through a competitive process. So you send us a proposal on how you'd like to use quantum computers, and one of those is the IonQ platform, which we're very proud to have access through our Quantum Computing User Program. So strong partnership with IonQ over the last few years, and looking forward to having IonQ QPUs in our future high-performance computing systems.
Great. Thanks so much, Shaun. Let's talk a little bit about why this matters. Like, why is this important? And I think, Rima, maybe we'll start with you, if that's okay.
Yes, so this really matters because we're looking to solve very complex problems. And these complex problems take bringing together a group of people to make it, and a group of technologies and solutions to make it work. So first, you need innovative leaders that know that these tools are very powerful, and that to start applying them for real world applications. And we're so fortunate to work with Janet and David Wade and EPB to really take some of these real world problems and look at how quantum can solve them. So looking at their workflows and finding the bottlenecks and figuring out which bottlenecks can leverage quantum in an effective way. But quantum alone is not enough. You really need to look at the whole workflow, and the workflow uses CPUs and GPUs, and our partnership with NVIDIA is very important. NVIDIA has built a lot of libraries and tools so that you can go seamlessly between CPUs, GPUs, and QPUs, and also working with Oak Ridge, where in addition to the long partnership that we have and them leveraging our QPUs, we also have built some algorithms around optimization, and specifically grid optimization, that will all come together to help us be able to solve these really important real-world problems. So thank you for everyone's leadership here, and I'm really looking forward to the results that we're going to have from this partnership.
And Nicholas, it'd be great if you wouldn't mind maybe add a little bit to that, if you could, around.
Yeah, for sure. I think the point that Rima made about hybrid applications is really spot on. So, you know, when you look at actual commercially and scientifically useful applications on a quantum computer, I think it's really critical to remember that those work in a pipeline that involves GPUs, CPUs, and quantum processors, QPUs. And that's maybe been obvious for a long time to people who are thinking about NISC applications, that you really need both of those kinds of hardware to work very closely together. But it's also true for any kind of application you can think of, even sort of ones we think of as being further ahead and more distinctly quantum, that you really need those applications to have subroutines that can go to either kind of machine. And so that's why we've been building a platform, and we've built a platform at NVIDIA, which this project has used and has been really great to see use it as well, called QWC. And our QWC platform is a programming environment that allows developers to work on applications that can very easily access those two kinds of hardware in a way that doesn't need you to know the details, the technical details of writing for that hardware in a way that you might otherwise have to, and also allows people to simulate quantum computers and test their ideas out before they have them. And so it's, I think, a real testament, this project, to just seeing how far we're going towards that vision of hybrid kind of accelerated quantum supercomputers. And I think it's been a great example of how partners are what make our work great, and we've loved working on it.
That's great. Thanks so much. You've got a room full of people here that have come to learn and have been on the bleeding edge of something really new, but they're really here to solve problems. So maybe, Janet, talk about the problem that EPB is trying to solve here. What's the focus?
Yeah, so I'm going to preface that to say I am not a quantum physicist. My background is I'm an electrical engineer that's been in the electric utility space for over 20 years. So what excites me about this partnership is being able to utilize the new technology with classical technology to help solve our core business, is the electric side. How do we make that more efficient? If you hear about grid optimization, a lot of times what you hear about is more of generation unit commitment. How do you turn on and off generators? So EPB is actually what we call a distribution utility. We don't generate our own power. We actually purchase our power through a company called TVA, Tennessee Valley Authority, and they deliver it to our distribution substation. And then that's where we take that power and deliver it through what we call circuits and feeders to the customer's home. And on our grid, we have over 200 circuits or feeders. And on each of those, and total between all those different circuits, we have over 1,200 smart switches. And what the switch is designed to do is to help sectionalize those feeders when there is an outage, so it helps reduce the number of customers who experience an outage. But those switches, what they also do is connect some of those circuits together for redundancy. So as we ask our engineers on the power side, we say, what is something that could help your job today that we could do to make it more optimal for the electric side? And so our engineers came back and said, well, when we connect all of these circuits right now together for redundancy, it's usually where one circuit ends and the other circuit starts is where that normal open switch is today. But that isn't necessarily the most optimal placement of where the switch should be at. So what we thought to do is to take a small pilot of a few circuits, a handful of switches, and do some optimization between hybrid computing to see what is the most optimum placement of where that switch to connect the different circuits together would be to help balance load, to help reduce voltage drop, and help reduce line loss. So that's the project that hopefully that makes a little bit of sense with the audience here, is what would really help a distribution utility.
Great. And maybe talk a little bit about the workflow, Shaun. How does this all come together?
Yeah. The really important first step in this whole partnership was getting our technical teams together. We've had a technical working group that's been meeting for a couple of months now. To sort of frame the problem. So Janet laid out the problem that we're trying to solve. So it's a real world problem, and a solution is one that could actually be deployed on EPB's distribution network. And so the way we're framed this and attacking this from a classical quantum perspective is EPB has lots of historical data about how their grid operates that we're going to leverage on the front end. We're going to use the NVIDIA DGX box to help do some data reduction on the front end to get that data down to a smaller set that we can work with. IonQ and the Forte system is going to be used to do the optimization that Janet mentioned. So this system, I think, has 36 switches, and They can be on or off, and if you do the full combination, there's like 69 billion different combinations of topologies that can be explored there. So it's a very nice optimization challenge that can be deployed and solved on an IonQ computer. And then on the back end of that, once you've identified the top few topologies or configurations to optimize for load drop or load loss and voltage stability and things like that, we'll use the classical NVIDIA system on the back end to do some power flow simulations to make sure that these topologies actually work and will be stable, so that an action taken by EPB, they can have confidence that this is actually going to work when it's deployed.
Great, and maybe this question really is for the rest of the panel, so we'll kind of run through this. But Janet, maybe you can start. But talk about what successful applications look like here. What's the future hold? What do you see?
Yeah, so this project we're excited about because it's something very useful that we're starting as a pilot at a smaller scale that we can scale out, because we have over 200 circuits, over 1,200 switches. So we hope to see that be able to scale out with our grid to help there. But there's so many applications on the grid side, from anywhere from preventative maintenance to fleet. We have line crews that goes out during outages. How do we route their route to most efficiently so they can help with reducing outages quicker for our customers? Lots of grid optimization that we can look at. So we are very excited about that. And this is only looking on the electric side of our business. We also have the broadband side that we could take a look at as well too. So there's endless potential for a utility with different applications.
You did an amazing job talking about how a utility can benefit from quantum. I'm just gonna take it a step up and talk about how anyone can benefit from quantum. So there are so many different applications for quantum across many industries. Just to name a few, in the pharmaceutical space, creating new drugs, in the manufacturing space, building new materials, in the financial services space, building new models that are cutting edge and help with risk, understanding risk. And also on the quantum side, quantum networking is very important, because everyone is vulnerable when quantum computers can break encryption. So also looking at quantum networking and how you can use it to protect your data and your network.
Yeah, I mean, I just want to make even more general point. We can get higher and higher level as we move down the panel, which is that these kinds of applications, it's amazing to see the progress that's made on investigating them when the right resources are available, which is, of course, what we're really interested in making sure of at NVIDIA. So when people have access to these hybrid resources, applications development, which I would argue is one of the big challenges we still have in quantum computing, is developing better applications, which is exactly what this project has done. And so I think that's a key point here, is to see how successful that can be. And that's why we work with our partners like quantum builders, with end users like EPB, and also with research centers like ORNL. We want to make sure that this work can be done, and it's great to see it happen.
And maybe, Nicholas, before you go, I mean, I think of NVIDIA as a hardware company, right? But how does this play out for algorithms and applications?
Yeah, so we do much more than build hardware. We're not like a chip builder. We build whole ecosystems around finding ways that compute can do things it couldn't do before. So quantum computing is a completely natural fit for us. And the work that we do isn't just providing hardware, like classical hardware for people to do that research on. We have the software platform I talked about, but also we work with partners on actually implementing that and solving those problems. And we do application development with partners as well. But everything we do, we're very central to the ecosystem, and we touch the whole ecosystem, so we do it all with partners. And we're very happy that that's the way it works.
Thanks so much. Shaun, you want to bring us home? Sure.
So in terms of looking at the future, I love this project and this partnership because it ties us to a practical challenge where we can use quantum and classical computing today to make progress. Oak Ridge National Lab, one of its pillars is high-performance computing, as you might assume, given our building these fastest computers in the world. Our scaling can only get us so far of classical systems, and we've kind of reached the limits there. And so our computing strategy is looking at heterogeneous computers. And that includes CPUs, GPUs, QPUs, and maybe other processors that are invented going forward. So this is a great project to keep us tied to some practical examples while we're working on this strategy. The next So we currently have Frontier, which is a CPU, GPU system. The next computer after that, which the Department of Energy will fund us to build, will have some quantum adjacent components to it. And then the one after that, we expect it to have inherently quantum processing units built into the high performance computing infrastructure. Because our goal is to build the best, fastest, most flexible high performance computers on the planet to solve some of the most challenging scientific problems, including things on the electric grid. The other thing that I'd love to mention is that quantum networking is a big research topic for Oak Ridge, and it's applicable to all of the folks on this panel. I see quantum networks as a platform to really magnify quantum computing, sensing, communication, et cetera. So we're doing a lot of work, future-looking work, to expand the reach of quantum networks, the distance, the quality of quantum networks. We're working on satellite communications for long-distance quantum networks, et cetera. So. And then finally, a big thing that we're focused on for the future is quantum materials. So quantum computers can be used to design new quantum materials or simulate through simulation and analysis that could inform the next type of qubit that comes out on a platform. But there's all kinds of other applications for quantum materials. So we use our spallation neutron source and our high performance computers to help develop what is that next generation of quantum materials for all kinds of applications, including computing, sensing, communication.
Thanks, Shaun. I think we've got a little bit of time to take some questions. So while y'all are formulating questions out in the audience, I'm going to ask Janet a question, and then if folks want to raise their hand, I'll bring a microphone out. But so Janet, you have effectively the first commercially available quantum network and quantum computer coming here in early 2026. What's the process look like for entities that are interested in kind of leveraging you guys as a test bed and kind of thinking about it as a partnership?
Yeah, thank you, Charles, for that question. I talked a lot about why it's important for us to build application to help support the grid. But the other piece why we did this is we feel that quantum is that next wave, that we want to help accelerate that space. So our infrastructure is commercially available. So on the networking side, if you have products that you need to test out, you can go to our EPB website, quantum website, and come talk to us on how you can come test your product on our network. And then the reason we have the computing is also it's going to be our hours are going to go into an EPB cloud similar to AWS. And so you could utilize, we hope that researchers, academia from all over the nation to be able to use some of our hours to do advancement on your algorithm testing. So we offer the networking and computing as commercially available. And Kirk is right there, is our business strategy there. So if you want to learn more about how to utilize our infrastructure, we would love for you to come visit us and do that. So thank you, Charles.
Absolutely. Any questions for the panel?
Hey, Amy Orton-Smith, British government. Nice to see a fellow Brit, I assume, up there on the panel. Obviously, I look at it from a public sector perspective, so I'd be really interested to hear if there was any public sector involvement in what you've put together in Tennessee. And congrats, by the way, it sounds amazing. I'm loving the grid application case that you're highlighting here today, Janet. Fantastic to hear. And then just to talk about how you can engage these wider communities. This is a theme that we're hearing a lot of during the course of Quantum World Congress: community engagement and partnerships. So when you've thought about those 2 points, the other one I'm super excited about is hearing NVIDIA working with partners to develop the tech, and it's not all sort of single stack isolationist activity. So yeah, great to hear.
So I think if I'm hearing the question correctly is how are we involving the private public sector in that? So I feel like it's almost a Charles question on here. The Chattanooga community is very collaborative. And so, we started kind of more of the private here, but we want to include even industries in our community. And we're planning on doing a summit early next year to be able to bring in industry to see what kind of applications that you can utilize our infrastructure, work with private partners. We work very well with academia within our local community, there's lots of academia within the state and out of state that have reached out to us to say, how do we partner with that? So we believe in the true ecosystem. So I would love for you to come join our next panel at 4 o'clock today that Tashia is going to be moderating later today in the classroom. And we're going to talk more about kind of how do you build that ecosystem. Yeah.
And
Just to add on to that a little bit, so Oak Ridge National Lab is a federally funded research institution, right? So we have a $2.6 billion annual budget that from government sources primarily that fund research across all kinds of science, but quantum, computing, the electric grid, all of those are big areas of federally funded research. And so we would not be able to do the things that we're doing with EPB, IonQ, and NVIDIA today, or many other customers, without a huge amount of public investment, public money investment, federal investment in the case of Oak Ridge. It's allowed us to build the technologies that we then look to transfer out. That's part of the mission of the labs, is to transfer that technology out to have economic benefit for the nation. It's in our mission to provide economic benefit. So that's another way where public-private partnerships are key to success.
Hi, thanks everyone. My name is Hossein. I'm a physics person. So what I'm hearing here, sorry if the question is dumb, but I'm assuming that it's mostly end up solving some optimization problems, even in drug, pharmaceutical, or anywhere else. And I'm assuming that what's happening mostly using quantum algorithms and solve it on high performance computers, not actually on quantum computers. Correct me if I'm wrong. But it would be great if you probably have some numbers. Say, for example, we have this problem, optimization problem, with trillions of data or variables, for example, unknowns. We could solve it on this quantum computer with, let's say, spending some dollars on time, which is not possible to solve it like classically. If you send me, for example, some of those numbers, that would be great. That would attract a lot of academia, because people in academia, they like to see numbers. Okay, does it worth to do with it or not? But that was a great talk. I appreciate that. Thanks.
Can I just say a few things? Okay. Thank you for bringing this up. So to answer your first question, optimization is a very key area for quantum, but also simulation, quantum machine learning, bringing quantum and AI together. There are many problems that you can solve. The goal is to solve problems you cannot solve on classical computing. And actually, we are at a point right now, like for example, with our quantum computer, you cannot simulate anymore a quantum computer on a classical computer. So now you can work on problems that you can't really work on a classical computer. And when the quantum computers are small, the main goal is to try and find what kind of problems they can solve and show some narrow advantage, knowing that that same algorithm you can move to a larger computer and show broad advantage. And that's coming really fast. So now is the time to be working on the problems, figuring out what kind of problems you can solve, and figuring out how they all fit into your workflow. And the goal is absolutely to solve problems you're not able to solve today, or else, why do you need? Then it's just a cumbersome new tool. But it will solve it faster, better, more accurately as you put it into the hybrid workflow.
I think this is a really great, this is the question, right? This is the question that everyone should ask. And I think one of the important things as well is, historically, it's very difficult to compete against classical hardware because there's heuristics, and because, when you set the bar higher, then people reach the bar, or try to reach the bar, right? So, but I think there's really a move, what's been really exciting is in a shift in the way people think about this as it being a quantum versus classical, but more like, what can you do when they come together, like we've been talking about? And that hybrid model is actually the model that you need to try and beat with a conventional computer. And when you think about things in that way, I think it becomes less like there's two competing technologies, and it becomes much easier to see a world in which you add something to what you were doing before, as opposed to have to completely rewrite or compete with it in what seems like a completely confrontational way. I'm not giving you any kind of concrete input, but I think that's an important shift in thinking that is going to make us realize that maybe what we're trying to do isn't as hard as we thought when we think in those terms.
Thank you so much. I think we are out of time, so if y'all would please join me in a round of applause for the panel.